Good afternoon, folks. Did you like my CAT scan there? Look at this crowd. Amazing. You know, the weather's nice out, guys. I mean, and you're here. This is actually part of the Big Ideas series. Tracy mentioned that. This is actually the biggest idea. So you've made it to probably one of the most advanced and really out there on the edge presentations of the entire festival. And I say to you, welcome, Earthlings. We are friends here together. It's so great what Brian and Tracy have done here. I mean, I don't know if you've been participating in the festival so far. I mean, I think Brian Greene is channeling Simon Cowell in a sense. I mean, the gala this week was American Idol with Stephen Hawking and Philip Glass. I mean, it was just incredible. The idea that they would imagine that there's a hunger in New York and around the world for these kinds of events, and then to actually pull it off is extraordinary. Tracy, every year I think she's channeling Jane Fonda. I mean, this is a great sort of set of ideas from two real visionaries, and this is an extraordinary event in the city of New York, and I just want to say hats off to them. So let's get a feel for the audience here. We are at the new school. How many Republicans are in the audience? Couple, okay, good. How many Democrats? Raise your hands. Right. How many Spartacus Youth League? Any? Couple of hands went up. Great, good. I'm feeling good about that. How many are pro string theory, super string theory here? Raise your hands. Okay. How many anti? How many anti? See, there we go. Look at this. Look at this. How many crowds like that do you have in New York? So we are going to fully explore the theoretical implications of the LHC, which is the what? Excellent, excellent. You're also going to learn about CMS. You know what that is? Well, you will learn. How about Atlas? Alice? These are some of the experiments, and some of you are calling it out. We're going to learn what the various detectors and experiments are that are going on at the LHC. How many of you have a sense of experimental science or experimental physics in your background? How many of you owned a microscope? Anybody own a microscope? Yep, telescope? Sure. Cloud chamber? Hey, what? Cloud chamber's funny? Yeah, see, we got some. I mean, the idea that this invisible world of either outer space or astrophysics or the subatomic world is not open to us is, of course, belied by experimental physicists who have to find ways, find windows for us to make it inside the atom, to detect the various particles that are implied by the standard model. And, of course, there's been down through the history of physics this tension between experimental physicists and theoretical physicists. I mean, a very, very long time ago, before the Copernican era, I mean, physics was about guys, almost exclusively guys, sitting around thinking up stuff, running it by the Pope. If the Pope said it was okay, we go with it. You know, that was theoretical physics back then. Then, after Galileo created experimental devices, in his case the telescope and others to follow, to actually look at the way the world was beyond our vision, the models began to change. And then, you know, all the way to the beginning of the 20th century, when the standard model came in, and really experimental physicists were left in the dust because the theoretical models were really untestable. And that's kind of where we are today. And really the LHC, the Large Hadron Collider, is a way for the experimental physicists to catch up with all the theoretics that have been done in the 20th century and the early 21st century. And so we have an extraordinary moment where it's possible to test some of the most amazing elements of the standard model that have never been tested, plus the theoretical models that are implied by things that have never had any sort of experimental tests, superstring theory, supersymmetry, things you're going to hear about today. So the LHC is a great moment in time that brings experimental physics and experiment design back into physics with the potential of seeing things and places and having understanding that we've never had before. So, first of all, what is this big idea, big thing, this LHC? It doesn't fit in your basement or your garage. You couldn't make one on your own, and here's why. Roll the video.
At the very beginning of the universe, it was extraordinarily hot. There was this amazing soup of hundreds of elementary particles, photons and protons and quarks and Higgs particles. It was floating freely. And then the universe continued to cool and expand. The action from a particle physics point of view all took place in the first 3 minutes. Many, many interesting mysteries happened at that time. And amongst them was the beginning of all the structure in the universe. So the really deep goal of particle physics is to explore the next frontier in energy. So we created the Large Hadron Collider on the border between Switzerland and France, about 100 meters underground. Huge international collaboration of scientists and engineers with the goal of trying to understand the energy frontier. Each time I've been invited down and go into the accelerator pits and see the detectors, and you feel like you're going into a mine or something because you go down in some little elevator in a cage. It's this huge cavern-like thing. It's not rough and raw, it's a real concrete building. And you see this huge detector there that's becoming more and more mammoth, something like 4 or 5 stories high. The tunnel is very long, it's something like 27 kilometers. Basically, they're making a head-on collision. When these particles collide at extraordinarily high energies, you actually, for a little while, create this primordial soup that was like at the Big Bang.
We have finally got the beams into collision at 3.5 TeV per beam. I think we're all very emotional, very happy. This is the first real important milestone that we have for starting to do discovery physics in LHC.
In previous years, people were satisfied to just be able to describe what nature is actually doing. And now we find ourselves trying to make sense of it.
So, a couple of things that you notice from the video. The scientists at CERN, they actually do move that fast when they're working. But they won't be moving as fast as that on stage. And Steve Meyer's there talking about them actually achieving some of the first experimental results. That is actually him being emotional there. That's I've never seen him that emotional in my life. So at this presentation, we are deliberately going to stay out on the edge of theoretical physics. And so there may be points at which you feel a little bit lost. You should embrace and feel a little bit excited about that, because I think the panel that we have here today truly will explain in the terms that scientists understand a lot of what's going on. You'll understand plenty of what's happening here. But if there are a couple of moments when you don't, I'll try to pull us back a little bit. I will fail, okay, at certain points, but that's what's exciting about these events. So please, without further ado, let's welcome the panel on. I will begin one by one. We have current and future Nobel Prize winners on our panel today. Jennifer Klay is an expert in high-energy nuclear collisions. She helped discover the phenomenon of jet quenching, which she will explain with us, in nuclear collisions with the STAR experiment at Brookhaven. But she helped to develop the upgrade detector for the ALICE experiment, which she will explain, at CERN's LHC. Dr. Klay is assistant professor of physics at California Polytechnic State University at San Luis Obispo, and she was a staff scientist at Lawrence Livermore National Laboratory before joining Cal Poly in 2007. Please welcome Dr. Jennifer Klay. The man needs no introduction, but insists on one. Professor Frank Wilczek is one of the most brilliant minds at work in theoretical physics today. In 2004, he received the Nobel Prize in Physics for the discovery of asymptotic freedom in the theory of the strong interaction, which, if we're lucky, he will explain to us today. His most recent book, The Lightness of Being, Mass, Ether, and the Unification of Forces, was published in September 2008. He is a product of the New York City Public Schools, ladies and gentlemen, and presently the Herman Fischbach Professor of Physics at MIT. Marcela Carena has worked closely with experimental physicists at Fermilab and at CERN, and has developed strategies for discovery at all of the most important high-energy particle colliders around the world. Dr. Carena has developed an extended theories to explain the origins of matter and mass. She's a senior scientist at the Fermi National Accelerator Laboratory in Batavia, Illinois, and a professor of physics at the University of Chicago Enrico Fermi Institute. And finally, Dr. Monica Dunford is an experimental high-energy particle physicist who helped bring the ATLAS detector at CERN into operation for the LHC. Her areas of expertise range from searching for new physics particles like dark matter to calibrating the ATLAS hadronic calorimeter. And I hope she doesn't explain that to me. She crawls around in small, dusty places while connecting some of the 3,000 kilometers of cable in ATLAS, and I hope she does explain some of that. Dr. Dunford is currently a research fellow at CERN who lives full-time in Geneva, Switzerland. So, Frank, let me start with you. I described crudely this tension between experimental physics and theoretical physics and how it's been difficult for experimenters to keep up with the theory. Where are we now, and how important is the LHC? Do you really need it, or could you just do it all in your head?
Well, theoretical physics had a great leap of synthesis in the mid-1970s. With the development of what's called the Standard Model. And many of us who were involved in this thought it was kind of a ramshackle structure that would be improved rapidly, but it's turned out to be much more successful and resilient than any of us realized at the time. And experimentalists who've been trying to get beyond it and discover phenomena that aren't described by the Standard Model have just succeeded in intervening years in showing how accurate and correct it is. But the Standard Model, as it stands, is kind of lopsided. It's not as beautiful as it should be, given how much of the world it describes. And we've got some beautiful ideas for how to improve it. Make it more symmetrical, make the equations more beautiful. And some of the ideas are fairly concrete, so they're in a form that's ready to go, ready to be tested. And the LHC is the tool we need to see if those ideas are right.
Well, we certainly have in our minds the images of that huge thing, the giant ring and the sets of rings underground. Jennifer, describe just what the machine actually is and how it works.
Well, so as you said, it's 27 kilometers, so that's 17 miles in circumference. But when, I think we even have an image we can bring up.
We have tons of images.
When you look at the actual tunnel, you can see that white circle is kind of telling you where the tunnel is, but it's deep underground, so there are actually people living in communities on top of this accelerator that goes under their homes.
And livestock, too.
Yes,
yeah.
yes. There's farmland and all kinds of things. And there's an image showing the underground. There are actually 4 experiments at different locations around the ring. And basically what it does is they accelerate particles, and they can do different kinds of particles. So proton collisions, where they send protons around in 2 different directions and collide them in those 4 locations. Or they can do a heavy nucleus collisions, and that's actually my area of interest. And we're going to be looking at those in the ALICE experiment. I think there's even a nice little video that shows what happens as the particles go around.
Well, before we do that, let's just talk about the tunnels inside the tunnel, because there's the big tunnel, and you can sort of see where the humans sort of walk around. But then there's a smaller channel within which is a medium for actually accelerating the particles. Explain what is required for that medium, like right here.
Yeah, so basically it's a series of very powerful electromagnets. And you use powerful electric and magnetic fields. The electric fields you use to actually accelerate the particles to make them go faster. And then the magnetic fields are what bend the particles around in the circle. And the LHC itself is actually, it's the largest and coldest refrigerator ever built, because the magnets require so much power. They have to be run as superconducting magnets, and you have to run them at actually minus 450 degrees Fahrenheit in order to be able to get them to the very high energies they need to be at to bend the particles in this beam.
So what I don't quite understand is, Frank and his buddies come up with this crazy standard model, and then some other physicists go to people in France, and I guess for a while this was going to be in Texas, and say, to test Frank's wacky ideas, we need a 400 degree below zero refrigerator in a 27-kilometer ring dug underground. Figure it'll cost us about 10, 11 billion. Let's build it. Is that a hard thing to do?
Well, yeah. There's been an evolution over many years. So this is not the first particle accelerator ever built, but it is definitely the most complex and complicated machine. And I think basically over the last 50 years, the technology has been developing and improving to the point where we can now make a machine of this type and finally test some of these theories that we haven't been able to until now.
And as it was said in the original video, the idea is that by smashing stuff together like this, and again, my beginning in physics was smashing golf balls with a hammer, and so the fun of smashing stuff to discover new things is absolutely intuitive to me. But what she's saying is that in the video was that you create for a moment the sense of this primordial soup in the first 3 minutes of the Big Bang. Can you explain a little bit how that happens, Jennifer? And then I want to get some other.
Yes, I'm actually flattered that you would ask me to explain this, given we have Frank here.
Well, Frank will correct you, I assure you.
Well, let me correct you. It's not the first 3 minutes. It's the first thousandth of a second.
That's right. That's right. So yes, and the first millionth of a second after the Big Bang, I mean, the particles that were what made up our universe were quarks and gluons. These are basically the particles that are inside of all of the atoms that the rest of us here are made from. And it's actually his theory that says that they here we go, there we go. So you know that we're made of atoms. Atoms are made of a nucleus and an electron orbiting around that nucleus. And the nucleus itself is made of what we call nucleons. But those are actually composed of even smaller particles. If we go to the next one, so the proton and neutron are the particles inside the nucleus. And then the quarks and the gluons are the particles deep inside of there. And it's Frank's theory that explains why those quarks and gluons are bound together in these particles.
And they've been bound since the first thousandth of a second of the Big Bang.
That's right.
So they haven't been kicking around independently for quite a while.
That's right.
And so you're going to try to bring them back a little bit.
Exactly. So the idea is with these particle collisions, we can actually smash the nuclei together and liberate those quarks and gluons for a brief moment and see how they interact in this primordial soup. So we can try to learn what happened as the universe evolved into what we are now today.
All right, Jennifer, hold on with that thought, because I do want to see that animation that shows how the particles get sped up. But really, the speeding up of the particles and the adding of energy to the various kinds of particles is just the beginning. You have to detect what happens in the collisions, and that is where we get to your 3,000 miles of cable. And tell us about the various experiments, and there are really just a few that test and look at what's going on.
Right, so this is one of the experiments. This is the ATLAS experiment, which is what I work on. And you can't see any people in this picture, but actually this experiment is 7 stories tall. So the inside of that is about 2 times, in the inner part there, you have is bigger than me. And the idea is that, you're talking about very, very small particles, and they're colliding, and in very, very small, in the sort of micron size in the center, and yet you have to build a 7-story experiment of this size in order to be able to detect all those particles. And the point is because you're basically taking 2 very light, small particles, smashing them together with very high speeds, very high energies, and out of that, as you might imagine, which is very satisfying when you smash 2 things together, is a huge amount of stuff. And so it's a very dramatic collision, and you get stuff spraying everywhere. And you basically need an experiment of this size to be able to detect all the particles that come out.
Now when you say stuff, I mean, I believe that the number is something on the order of 600 million events per second that you have to be able to detect?
Right. So what we do is we.
I have 5 kids. You know, that's it's enough for me.
Yeah. So the beam collides 40 million times a second, and we have to be able to detect every single one of those events. So not only do we have a lot of stuff, we're trying to detect the stuff very, very quickly, and a lot of the electronics that we have is therefore incredibly fast, incredibly precise, because we have to be able to know within 25 nanoseconds. If that, be able to detect that particle, measure that particle, know what collision that particle came from, determine, what that type that particle is, how much energy it has, and all that kind of stuff has to take place within 25, in this very short period of time.
25 nanoseconds.
25 nanoseconds.
So it's more complicated than tagging penguins and following where they go.
Yeah, exactly. Yeah. I would say that. Well, just slightly more complicated.
Slightly.
Yeah.
All right, and Marcela, you're at Fermilab.
Correct.
Now, I've been out there. That's a pretty big, that's no slouch of an accelerator.
Yeah.
What can LHC do in terms of dimension or energy or whatever that gets beyond Fermilab?
Okay, so, well, Fermilab is running at the moment, the same as LHC is starting to run, and Fermilab is kind of at the end of its period. And instead of being a 70-mile circumference, Fermilab is a 4-mile circumference, so it's like the little brother. And we measure kind of energy in terms of many times the mass of a proton. So Fermilab collides a proton and an antiproton, and each of them has an energy of 1,000 times the mass of a proton. LHC instead is going to collide a proton against another proton, and they will have 7,000 times the mass of the proton. So it's basically 7 times more powerful in energy. And the idea is that because energy is equal mc squared, if we have more energy, although these protons are going much faster, the idea is that at the end we will be able to produce particles that are much heavier than the ones that we can produce at Fermilab. And in fact, at this moment, of course, both colliders are trying to find the Higgs, and I don't know
the
how.
Higgs. Well, the mystery of where is the Higgs we'll get to in just a moment.
So this is the race for the Higgs at the moment.
Yeah.
And with my
we could have called this whole session race for the Higgs rather than back to the Big Bang. But that's another story, and we'll get to it in just a second. Let's look at that animation, Jennifer, that you talked about that actually gives us a sense of what the particles will be doing and where they'll be going.
Sure.
It'll come up here in just a second. And basically, we use the magnets, the supercooled magnets, in the channel that you talked about
That's
to
right.
get them going. All right, here it is.
So here we go. We've got some protons that are initially accelerated in 2 smaller accelerators and then boosted into a larger one and finally injected into the Large Hadron Collider, which is that largest circle. And you send some in one direction and some in the opposite direction, and they go around 11,000 times a second. And at some point collide inside of a detector like this one is Atlas. And when they collide, as Monica mentioned, the particles that come out of those collisions need to be detected by these 7-story tall machines. And we try to collect as much information as we can about those particles so we can recreate and reconstruct what happened during the collision itself.
Now, Frank, when you look at something like this and realize the scale of how many collisions have to be detected, I suspect there's some sort of printout that comes out and you sort of see the number of events that happened and you know what's significant and what's not. How do you keep the collisions that are happening there, which are what those lines are, from mixing up with just noise in the environment? Maybe a cow moos or something on the top and that gets onto the... I mean, these things are very, very sensitive, but there's also stuff happening around.
Well, there's not stuff of this particular kind happening. You're concentrating enormous amounts of energy in a very small place, and you know where the place is. So although, for instance, there are cosmic rays coming down from space, they would look quite different in these detectors.
So it's very easy to strain out the noise and focus on the important signal.
Depends what you mean by noise and signal. So but what is true in the spirit of your question is that the vast majority of the events will be just reproducing the physics that we know. They will be governed by laws that we already know. So to pick out what's new, new things that aren't already in our equations, we'll have to have very good ways of filtering out the old things that are already in our equations. So I don't know, maybe 1 in a million events or 1 in a billion events will have something that's not described by the equations we already know. And that's why you have to understand these kinds of pictures and the data that goes with them extremely well in order to find the needle in the haystack.
And from my perspective, Monica, I mean, you know, proton hits a proton and it does something sort of boring, you know, like Frank's theory suggests. I'm pretty excited.
Right.
I'm pretty excited. But you're really looking for the, as Frank says, 1 in a billion events. How do you calculate the probabilities that the things that you're looking for are even going to occur, and how do you design detectors to you know, detect those probable things from happening?
Well, I mean, so Atlas, of course, is 7 stories tall, and actually started thinking about this experiment in 1979, I think, was when we started about it. So it's actually even a bigger question than what you think. It's because what we have to be able to do is we have to be able to detect any physics that Frank is going to throw at us in 30 years or 40 years, right? So it's a much larger scale program than not just sort of like Frank comes up with a theory, we test it tomorrow. That's not, I mean, this is too big to be able to do that. And so what we have to do is we design the detector to basically to be able to detect anything that comes at us.
So it's like a net. You need to make the net wide enough to envision almost anything that even the theory won't explicitly predict.
So, yeah, so what we do is we usually go back to the basics. So like Frank's got his crazy theories, but usually what happens is that they're not crazy. This is the experimental theory.
Nobel.
You're thinking of somebody else.
So we got these crazy theories, and but we kind of go back to basics because the detector, usually all these new particles, they end up decaying into particles that we know. So for example, you have a new, let's say dark matter, you have a new heavy particle that's being predicted. That particle will decay into something
All right,
that
yeah, let's look at
know.
this slide here. This is actually a great representation of the various kinds of things you're looking for and how the decay takes place.
Right.
All right, a photon.
Right, so it decays in things like photons, and then we have these different layers of detector to be able to detect different things. So we have a tracking detector, for example, that detects charged particles. So you'll see we have photons aren't charged, so they don't show up in the tracker detector. We have electrons are charged, so they show up in the tracker, and so forth. So, and then in the next layer we have what's called, well, we have 2 layers of calorimetry, and these measure the energy of particles. So you can see that the different types of particles, a photon versus electron versus a charged hadron, they deposit energy in different ways. And then you also have this muon, which is kind of a fat electron, and then it sort of just zips through the whole detector, and we have a dedicated detector for that. So each of these known particles, and the previous experiments like Fermilab, we measure the same type of particles, photons, electrons, pretty much the unexotic.
So photons,
nanobots.
Electrons, they're easy. Charged hadron, you're starting to get into something that's...
yeah, it's very difficult to distinguish between those two. You can see that they tend to leave a slightly different signature in the tracker, and that's really kind of the only way we can distinguish between them. And then
and these bands here, where it says tracking detector, electromagnetic calorimeter, hadron calorimeter, and muon detector, do these represent also different energy levels, that it takes a higher energy level to detect something in the hadron calorimeter?
Right.
Yeah,
For example, so usually if you have the design of a calorimeter is you want to basically stop everything because you need to measure its energy. So you put huge amounts of material in there. So like, for example, in Atlas, the material we use is lead or iron. And so the particles are trying to be stopped. So only the most energetic particles travel farther because of the less energetic particles are being stopped. So what we end up detecting in the experiment at the end of the day is really particles that we already know, particles that we've seen that are around every single day.
Ruling out the boring stuff. Right.
Ruling out the boring stuff. Even the boring stuff kind of decays in this, produces the same type of particles. So what we try to do is we try to measure each and every one of these particles extremely, extremely well so that we can reconstruct the new particle that they came from in the center. We don't actually detect the new particle, we detect only its products.
These new particles are expected to be very unstable, mostly. So they decay into this stuff, and you have to reconstruct.
Okay, so Atlas is one kind of detector. CMS is another one, right?
CMS is another. It basically operates under the same principle. So the reason we built 2 was because, as I said, we have a program that's lasting many, many decades. And you don't want to, so the stakes are high, and you don't want to have, because the detectors are so big and complicated, you don't want to say, oh yes, look, we've discovered this, and it turns out that it was simply an artifact of the detector itself. So we have two detectors which are similar yet different. So they're similar in the sense that they have the same basic, they have tracking, just like what was shown there. They have a calorimeter, or they have a muon detector, but they're designed in a completely different way.
But it's like getting two sources in journalism, my silly profession.
Yeah, exactly.
You get two sources. You believe it more if you can confirm it independently, right?
Exactly.
So that's what the deal is. All right, what about the ALICE experiment? What's that about, Jennifer?
So ALICE is designed to look at nucleus-nucleus collisions, and we have sort of a different perspective on what we're trying to investigate than ATLAS and CMS. So it is still constructed from the same basic elements as what Monica mentioned. So here's an image of ALICE. I don't think ours isn't quite 7 stories. We're maybe closer to 3 or 4 stories. But it's using 18 different technologies, but around those same fundamental components that were mentioned before. And we're trying to really look at the evolution of this primordial soup. So rather than looking for new particles, what they're doing in the other experiments, our goal is to basically reconstruct the phases of this matter that we're creating in this primordial soup, going back to the Big Bang.
And let's just talk about phases of this primordial matter. I mean, in theory, if you can create this first 1,000th of a second of the Big Bang, in the same way that water becomes ice as it cools, you suspect that the nature of matter changes as the energy level changes, and that might be observable in some way.
That's right. In fact, we have observed it at the Relativistic Heavy Ion Collider at Brookhaven National Laboratory, which is where I did some of my research work before moving to the Large Hadron Collider. And what we know from experiments there is that we can create this primordial soup, and it's very dense and interacts very strongly with the quarks and gluons that traverse it. And it's a very high temperature medium. And basically, in order to create that medium, we start with nuclei that, in our understanding of the phases of nuclear matter, a nucleus behaves much like a liquid drop. And so we're basically taking 2 liquid drops and colliding them at very high energies and trying to boil it essentially into a steam of quarks and gluons. So kind of like the phases of water that you mentioned, we're trying to basically make steam. And then watch as those particles in the steam condense back into water and freeze into the particles that we
But literally, in terms of the kinds of detectors and the things that you're going to be looking at one energy state, you'll see a certain census of gluons and muons and particles, and then as the energy state changes, they'll disappear because they've combined and become other kinds of particles, and as the energy levels go down, the particles change because they combine or decay in certain ways.
That's right, and we never actually observe the quarks and gluons by themselves. We only observe the products that come from them after they've frozen back into those normal particles. And what we have to do is basically try to look at that debris and the patterns of the debris and reconstruct whether and what the phase looked like at the point when it was quarks and gluons.
Do we have that animation? I mean, the one that, excuse me, because I'm just a regular human, the one that was like totally awesome of the smashing.
Oh yeah, so we have an image showing
the totally awesome one.
collision.
This, I think, gives you a sort of a visualization. Marcel, okay.
There we go. So the white and the red are the protons and neutrons in the nucleus right before it collides. And basically, they look kind of flat in that image. I don't know if we can replay.
Yeah, let's do it again. For totally awesome stuff, maybe a couple of times.
They start off flat because they're moving so fast. They're at what we call relativistic speeds, that they've been kind of squashed by relativistic effects into these flat pancakes.
Close to the speed of light.
Close to the speed of light, that's right. And then what happens is you get the liberation of all of these quarks and gluons from, in this case, the picture shows the protons and the neutrons in white, and all of those colored particles represent the quarks and gluons coming out of that collision.
And in that mess of color there, there are particles that you know exist, right, Frank?
Yes.
And in the soup, maybe some characters that you'd love to meet. Right?
Yes. Yes.
Right. Okay. All right. So the energy level allows you to get beyond what we know into some particles that maybe aren't even predicted explicitly by the theory.
That's right. And also regimes of behavior of the particles that we think we know about where we can't solve the equations.
All right. So correct me if I'm wrong, Marcela. We've got a set of detectors that actually can detect the products of decay of individual particles that collide and smash apart. And we've also got this sort of primordial soup creator, which gives us a bit of a snapshot of the early parts of the Big Bang. Within that, what are the essential mysteries that you want to solve?
Okay. So, well, there are a couple of different parts there. One of the things is that we are detecting, as you said, as Monica was explaining, particles at the different layers of the detector. But one of the things that is very exciting and we hope to discover at LHC is the nature of dark matter. And
dark matter.
Dark matter.
Right.
And the way we expect to see dark matter at LHC is basically by looking at the imbalance between all the energy we put in and all the energy that we get out. If the amount of energy we put in and the amount of energy that comes out, there is a difference between them. That's what we call missing energy. And this is the way we expect to detect dark matter at LHC.
Now, it wouldn't be because there was some error in your calculation.
Well, well certainly not. No, not in my calculation, no. No, there is a bit of, people have, I'm sure, heard about neutrinos, okay? Neutrinos are very light, okay? The lightest of the particles we know. And of course, those neutrinos are also very weakly interacting with all what we know. So those neutrinos will appear as missing energy in our detector. Okay, we won't detect them. We
that was in the slide before at the bottom. You saw the neutrino go across, and it looked like you can't.
You can't do anything.
Those. Nothing happens.
No, nothing happens. So they're invisible. The LHC neutrinos are invisible to the LHC.
Correct. Yes. Correct. However, we understand the standard model and the neutrinos as part of it sufficiently well that we are able to compute what is the missing energy that we are expecting from neutrinos. So we can subtract, okay? So as Frank was saying, we need to subtract what we know from what we expect to be new.
Right.
So if we subtract what we know from what we expect to be new, we can subtract these neutrinos, this missing energy from neutrinos, and whatever is left as missing energy, as this imbalance between what we put in and what we get out, will be this explanation for dark matter. And we see there that dark matter is like 25% of our universe. And if you look at the ratio between matter and visible matter and dark matter, actually dark matter is about 85% of all the matter in the universe. And we don't really know what is it made of. We know that it cannot be explained by all the particles we know so far. So we are one. That's one.
That's one. Okay. So we get up in the morning, and the New York Times has this headline: "Scientists detect dark matter." It will be because there's a discrepancy between the energy going in and the energy coming out at one of the experiments that you just talked about there.
Correct.
All right. Tell me about the Higgs thing, and then I got to get Frank to explain to me what the basic physics are here, because I'm starting to get a little bit lost. You've got your slide detector thing. You got your slide.
Yes.
Clicker. Okay, great. So just hold on to that. All right. So let's go with the Higgs. The search for the Higgs.
Okay. So
because that's another big headline. We will wake up some morning and scientists either find Higgs or don't find Higgs, right?
Correct.
And that will be a big deal. All right.
So we know that, for example, within the proton there are quarks and gluons, as we were saying. And these quarks are of some given type, okay? But there are many more particles that we have been explaining through the standard model and we have detected in the past decades that go beyond what are the basic constituents of the protons and the neutrons, okay? And the electrons that are in the atom. So the point is that all these particles are like a zoo of particles, the lightest having a mass like an ant, let's say, and the heaviest having the mass of a blue whale. Okay, so very, very different masses.
Vast masses.
And we would like to understand the difference in mass, but more than that, we would understand how they acquire mass at all. So that's one of the big puzzles we have today. We don't really know how they acquire mass, all these fundamental particles.
And if we understood how these fundamental particles acquire mass, we understand things like gravity, which has been a mystery for maybe not? All right.
Maybe you have to go a step farther there.
All right.
We got baby steps.
But this idea of acquiring mass, going from energy to acquiring mass,
Yeah.
this process is at the center of the mystery.
This is at the center of the mystery in the sense that, we have an explanation. Within the standard model, we have an explanation, okay? And we think, to say it in a few words, that is like, basically, if you think about, the picture of firing a gun, a bullet from a gun, it goes through molasses and it slows down. And this slowing down is what we think about acquired mass. The same here, we think that these particles go through this cosmic molasses, sorry. So, and then this cosmic molasses is what we call the Higgs field, okay? And so this is the way we understand that particles get mass. However, how do we prove it is the second question.
You need to detect the Higgs field. You need to detect the Higgs particle.
The Higgs particle. And so this Higgs particle is very different from all what we have seen so far, okay? It has been elusive because it's clearly heavier than what we expected, so we need more energy in order to create it.
Hence the LHC.
Okay. Hence the LHC, but maybe the tevatron also has there is a possibility there. In fact, it's a very exciting time at this moment because, we have a real opportunity. The Higgs is supposed to have some mass between 100 times the mass of the proton and 200 times the mass of the proton. And so the tevatron has sensitivity to look at that mass range.
The tevatron is at Fermilab. Okay.
The tevatron here in the backyard of New York, means in Chicago, has the chance to look at the Higgs, or is looking now very extensively to the Higgs.
If the Higgs is lighter, are you more likely to detect it in Chicago?
That is not as easy as that. If the Higgs is lighter, it's much harder to detect.
Okay, so you want it heavier.
No.
Just trying to get a sense of rivalry here.
Yes. Okay, so let me put it this way. The Higgs, as we said, we are not going to detect a Higgs. In these very nice collisions, there is no particle that comes with a little thing that says I'm the Higgs. Okay?
Right, yeah, exactly.
So it doesn't say I'm the Higgs, it's just decays into particles we know. But depending how heavy it is, it decays to different particles.
I see.
And some particles altogether would be harder to detect than others. It happens that between 100 and 150, being a bit generous there in the range, it is quite hard because it decays mainly what we call boson quarks. One type of quarks.
Photon quark.
Bottom
quarks.
Bottom.
Got it. Sorry.
Bottom.
Excuse me.
I am the only one with a good accent here. I'm sorry. I thought
we had a
about
whole narrative of the Italian accent last night here on the stage, but
this is a mixture of Italian and Argentinian.
And Argentina, right?
Yeah. So bottom. I'm sorry. So it's much harder to detect. However, Fermilab, tevatron, and Fermilab here in the U.S. has I would say, a good shot to detect the Higgs in that particular mass range, in that particular decay. Also can detect higher masses. For LHC, the higher masses will come up easier.
And this is exciting because, I mean, if you have more than one facility, it's like having more than one experiment at LHC, it increases the likelihood that you're going to piece together an explanation for the whole mystery.
Well, it's also the case that, we're pretty sure that there is this cosmic molasses that's complicating the laws and making things move slower. And we're absolutely sure that it's not made out of any of the particles we know about. But it could be made out of several different kinds of things. There could be not just one particle, the Higgs particle, but a whole world of phenomena that's responsible for making this molasses. But whatever it is, we've been living in this stuff for eons without knowing it, and we're going to finally find out.
All right, take us through the standard model to the questions of cosmic molasses, Higgs, and
oh my gosh.
Some of the other stuff. I mean, we haven't even talked about supersymmetry yet, right?
Yeah, let me talk about that. That's what I have prepared here. So that's unification and supersymmetry. So can we start with the first one? Yeah, good. So as I mentioned before, we have this very powerful, very accurate, sort of embarrassingly robust account of how basic interactions work, the standard model. That's not as beautiful as it should be. It has 4 different forces in it and different kinds of particles. We'd like there to be one basic force and just one kind of basic stuff. Now, we can construct mathematically theories that put different kinds of particles on the same footing. This is called symmetry, where you can make transformations of the names of the particles, and they would obey the same equations. So if that's the case, you say you've had a unified account. That's sort of, it's just a matter of a convention, how you've named things, that really electrons and quarks are the same thing at a deeper level.
But symmetry refers to pairings of things?
No, symmetry refers to the idea that you can make transformations in the equations, say changing electrons into quarks and quarks into electrons. And you get different equations, of course, but they have exactly the same consequences as the equations you had before.
I see.
So you
so
can
no
make
matter how you arrange it, it all adds up.
It all looks the same overall. So the idea is similar to the way we say a circle or a sphere is symmetrical, because you can rotate it, and although every point is in a new place, it's still the same overall shape. So it's the same idea but applied to equations. So these are called unified. These are called unified theories that put together electrons and quarks and photons and gluons, and we can write down very elegant theories of this kind. Now, next slide. However, a crucial prediction of this kind of idea, if the forces are really going to be all the same, is that they have to have the same strength. At least after you peel away the complications of things like the Higgs field and look down at very short distances and high energies, the different forces should have the same strength.
And that refers to the two forces, the weak force.
This is weak and strong.
And strong force.
And you can see on this plot that if we start to peel away the corrections and look to, from what we see, wait, hold your horses there. You spoiled my joke completely. All right. Okay. We make these corrections, peeling away the effect of the Higgs field to see whether the basic underlying forces at the shortest distances and highest energies are the same force and have the same strength. We see that if we take the strong and weak interactions and make those corrections to the strength, that the lines do indeed cross. So that's encouraging. But on the other hand, you might say that two straight lines do tend to meet at a point, so it's not as impressive as it could be. But then we have a third force. We can make the correction. We can also compare that, and you see, almost, but not quite. They don't quite all unify.
Now, and this information right here, these graphs are based on experiments we've already done?
Yeah, the little circles on the left are the measurements of the strengths that we know about. And then by the kind of work that I got the Nobel Prize for, you can calculate how they change as you strip away the complications and go down to shorter distances.
And the idea is, again, that they unify at some energy level, and that all of these forces, electric, weak, and strong,
should come
are essentially
together.
Part of the same stuff.
Right. There's one underlying force that sees them all the same.
Would you call it force?
I would.
You could come up with a better name than that.
People sometimes, it's the same concept as the unified field theory that people have been dreaming about for a long time. Okay, so if we were followers of Karl Popper, who told us the goal of science was to produce falsifiable theories, we could declare victory because we made a theory that's not only falsifiable but even false. What could be better? But of course, given that it was kind of a near miss, we look for ways to truthify it, to make the theories even better, and hope that if we do that, then it'll actually work.
But if you got the Nobel Prize for it being false, what do they do if it becomes true?
Well, the answer to that is obvious.
There's YouTube. No one will ever see this again.
Right. So then, So even with the unification I talked about, there were still two different kinds of things. There was electrons and quarks on the one hand, and photons and gluons on the other. So the remaining step is to unify those two things. And this is possible using an idea called supersymmetry. According to supersymmetry, there's an extra dimension of space, which is not, however, a dimension you could move around in or fly spaceships through or anything like that. It's what's called a quantum dimension. What happens if you move in that dimension is that you change into a very different kind of particle, which would be very uncomfortable, actually. But you would change into a particle that has a different character. So an electron could change into a photon-like particle, or a quark could change into a gluon-like particle.
Is it that it changes, or that there is a pair of particles that are kind of channeling each other?
It changes. No, it changes.
It literally changes.
It literally changes. So the mass changes. A few properties stay the same, but so we can tell that they're related, but the mass changes and the spin changes. So to implement, that would complete the unification. But to do that, we have to introduce new particles. When we introduce new particles, then there's different complications to strip away. So we have to redo that calculation I showed you. And now we can go. Yeah. Keep going. Susie is supersymmetry. Keep going. And you see, if you do it with supersymmetry,
look at that.
Now it really comes together. So that's why I love Susie. And so far, I haven't even talked about gravity, but we can bring that in too. And gravity starts out much weaker than the other forces, but if you go down to these same distances, it turns out that it too unifies. So
now,
it's really tantalizing.
Right.
I'll show one more picture.
Okay, go ahead.
So here we are at the LHC. To me, this is the central issue of what the LHC is all about. Right?
And which one are you?
Which one am I?
You're holding the harp? You're holding the harp.
How are your
waiting
glasses?
for Susie.
No, how are your glasses?
Yeah.
No, that's me. I've jumped ship, been lured by the siren's song, and well, I hope it's Susie, but it might be somebody else. I don't know.
All right, so that's great. Thank you, Frank. That's
All right.
great.
All right.
So based on experiments we've already done and measurements we've already made of these various forces, the lines don't meet. But if you add this multidimensionality to it and work the equations that way, they appear to meet.
Yes.
But detecting that is sort of your job over here, right?
That's right.
So how are you going to detect either the multidimensionalities, I don't know about the business with the harp and stuff, but how are you going to design an experiment that's going to begin to test or confirm any of these sorts of predictions here?
Right. Well, fortunately, along with the theory comes the prediction of how it decays. Because as Frank said, these are very unstable particles, and so they don't last very long, and so they pretty much quickly turn into the particles that we know. And so what that means in a typical SUSY scenario, the way that actually manifests itself in the detector is you get two protons collide to produce a new particle, for example, that might be SUSY, and that particle, that SUSY particle will decay in some way. And usually the way it decays is very dramatic. And so it decays to a lot of very energetic stuff. So if we go back to the picture of the different standard model particles with the Higgs in the center, you'll see that these are the options of that has the options of particles that it can decay to. And basically what it does is it decays in a way that experimentally we really like. Because we really like lots of clean, high energy things. And so what SUSY particles sometimes, and this is just some of their decay modes, can decay to is these leptons, that's that sort of greenish category there. It can also decay to lots of what we call very energetic jets, which are basically quarks that fly off with very high energies, and they acquire other quarks, so they become sort of protons and neutrons and so forth. And so what SUSY looks like to us is a lot of electrons, a lot of very high energy electrons, and a lot of very high energy jets streaming through the detector. So
while the detector is detecting a lot of what Frank calls sort of the standard stuff, the boring stuff that we would expect to see, sort of one-on-one particles, that sort of thing. At a sufficiently high energy, if a Higgs particle in this sort of super SUSY symmetry state were to decay, it would actually have all of this, not simply some or a few. It would actually, it would be a much more,
Yeah, for the
a
most
lot
part.
of different kinds of particles would come as opposed
I actually
to.
have a picture of what a Higgs would look like in the detector. It's there's a black and white picture of the Higgs decay. This is what a Higgs decay would look like in ATLAS. So in this,
And that's a theoretical predict. That is
this is a theoretical prediction.
graphic sort of representation of what you think you're looking for.
Right, and so what you can kind of see here is actually really kind of, this is how experimental physics becomes difficult, is there's actually 4 distinct particles coming from the Higgs and a bunch of other particles coming from the rest of the proton collision that we don't care about.
Let me just get back here to primitive man. Now, at the center there, that represents the collision point, and then the spray coming off there
Right.
is the various things that that sort of represent these explosive particles that you're imagining
Right.
seeing. And then what's this ring around the outside?
So this is a cross section. This is like basically if you sliced ATLAS through
see.
the center. So the
that's just
beam,
the-
the beam is coming kind of into the screen and out of the screen.
I see.
And you've kind of just looking at this cross section of it. And at the center is the collision. And so the Higgs has collided there, and we don't see it. We only see its products. And it's decayed into 2 Z bosons. And those 2 Z bosons, which we also don't detect, has decayed into 1 Z boson's gone to 2 muons, and 1 Z boson's gone to 2 electrons. And so what you see is if you see these 2 lines that are coming out all the way at the end, those would be the muons coming from the Z boson. And if you see these 2 points, these little lines that are leading to this kind of Lego-like thing.
The bar-looking thing there?
The
Yeah,
bar-looking
okay,
thing,
right.
those would be the 2 electrons. And all this other stuff is just other particles that just came along for the ride and aren't really a part of the Higgs decay itself. And so we kind of, one of the things we have to do experimentally is get rid of all that other stuff and then try to find those 4 particles. So it's kind of like a double needle in the haystack. One is trying to find the Higgs particle out of those 40 million collisions a second, and the second is trying to find the products of the Higgs decay out of all the crap.
All right, so back to you, Frank. All right, that's hard. Now, you suggested earlier in the presentation that you're thinking this is a 1 in a billion kind of event. I'm doing some very rough math here. 600 million collisions per second you can keep track of, and at a decay rate of something like in the order of 20 nanoseconds, right? So how many sort of runs of the LHC do you need before you're pretty certain that it's not occurring here? The probability would suggest that over X number of collisions, we should see one of these guys at this energy level. At what point do you kind of say, man, we're not seeing it? Or there's something wrong with the detectors? Or, you know what I mean? Help me, Frank, or I'll mess up your slides again.
I think the time scale for discovery at the LHC will be from 2 to 5 years. We'll start to see really crucial tests of whether we need physics beyond the standard model, or whether we can home in on the Higgs particle or particles. So
But
that's
is that,
that's
right. And is that
Yeah,
time frame, and when you hear him saying, you said 3 to 5 years, something like that?
yeah, 2
Right.
to 3 to 5.
2 to 3 to 5 years. Is that a process of refining the detecting strategies, or is that it's going to take us 5 years of constantly doing these collisions before we would even expect to see one of these big decays? And
It's kind of it's both. On one hand, you have these very rare processes, and so you need to be able to take enough data so that you can collect that data. On the other hand, you're talking about trying to find something on top of a lot of other, standard model collisions that are going on at the time. So it really is, it's 2 things. One, getting the one sort of collecting Higgs events, and then the other is being able to get enough of the other type of events so that you can understand what those events look like, so that you can figure out which ones are which.
And then you have to get it confirmed, and it has to happen a
Right.
number of times so that you begin to see the pattern.
Yes.
Right. And
many of these predictions are statistical, so it's hard to tell in an individual event whether it might be a Higgs particle or an ordinary kind of process that could look similar. So sometimes you just see a statistical excess of events of a certain kind. So that's even more challenging.
And what about finding, I mean, what we've talked about up to this point, with I think a couple of exceptions, there's experimental evidence that suggests a lot of what we've been talking about, right? I mean, but at a certain point, the theory completely departs from experimental evidence, and you're trying to detect things that, in fact, are made up out of whole cloth,
Yes.
quite frankly. And Marcela, take us there.
Okay, so of course, one exciting possibility for new physics that could explain many of the puzzles that we have today could be supersymmetry. And in fact, I would like to add that supersymmetry is great to explain the unification of all forces in nature, but has also a very appealing bonus to it, that it provides for a candidate for dark matter. Okay, so within the standard model, we do not have a candidate for dark matter. Within supersymmetry, we do have a natural candidate for dark matter. And again, this will be observed at LHC as missing energy, as imbalance between what I put in and I put out. So that's one exciting thing about supersymmetry at LHC, that you will see this dark matter.
Is that the same as saying what we may discover is that there are a hell of a lot more neutrinos than we thought? Or is it more sophisticated than that?
No, it's not that. I
Okay.
mean, we know that, well, almost.
Yeah, no, I come to this festival to be wrong every year. Brian brings me in here, I'm wrong, that's what I do, and that's my role, it's fine, don't worry. All right, so anyway, there will be some missing something.
Okay, so neutrinos are actually a tiny piece of the dark matter, but are not, we know because of the structure of galaxy formation and so on, that this dark matter has to be kind of heavier and slower moving than neutrinos are. So we know that neutrinos, even if we have an infinite amount of neutrinos, we cannot really make the dark matter. We need something different from neutrinos, okay? So supersymmetry gives us that one thing that is different from neutrinos that could be the explanation for dark matter. So that's one great thing, okay? Supersymmetry also have the Higgs, so explains. In fact, supersymmetry, as Frank was saying at the beginning, not only have one Higgs, have actually more than one Higgs. So we will have much more fun there, and and also we have to discover all the other half of the particles that we have not discovered. So basically, we double the amount of particles we have seen. So that's one thing, and I think, in my opinion, supersymmetry is the most robust or beautiful extension of what we know so far. However, since we have been boring, the theorists, I mean, we have been quite bored for the last few years.
Underemployed.
Trying to, entertain ourselves, we have thought about more crazy possibilities. And one of these crazy possibilities is the idea that there are more spatial dimensions than the three we have seen so far.
Right, and so higher dimensionality and being able to detect higher dimensionality, and that in these very high energy states, it's more than just the dimensions we know. It's all of these various kinds of dimensions. How would you detect something like that? I mean, I guess when you're in primordial soup, you're starting to get close to some of the conditions that Marcela was describing.
Well, I think in the same way that we look for these other elusive particles, it's through the products of the decays. And you always have to try to take what your detector can see and build back to what produced those things that you can observe. And
by eliminating various possibilities, then you come up with the
Exactly.
ones that the theory,
Exactly.
begins to explain. There's a lot of talk, and maybe it's just crazy talk, that the energy levels in the LHC can actually cause the universe to rupture, and the whole global warming thing would be moot because there'd be no Earth anymore. What's the chance of that happening?
Basically zero. And the
Yeah,
way
but we're talking about hundreds of billions in nanoseconds. Basically zero is still a pretty large number.
I think as a scientist, if when you calculate numbers, even if it's 1 with 100 zeros after it, one chance in 1 with 100 zeros after it, it's hard to say it's absolutely zero. But when the probabilities are so low, it is effectively zero. So that's where my basically zero comes from.
Okay.
But we actually know experimentally that it's not going to happen because we observe cosmic ray collisions in the atmosphere of the Earth from cosmic rays coming from extragalactic sources all the time, every day. If you put your hand out, there are cosmic ray particles passing through your hand right this very minute. And many of those collisions are much, much more energetic than anything we're going to make at the LHC. And we've looked across the universe with the telescopes that we have and with all of our capability, and we've never seen evidence for something as violent as this prediction that it would swallow the Earth and destroy everything we know. So I think we're all pretty confident that we don't have to worry about that.
And your explanation of why the Earth isn't going to be torn away?
Well, I think that empirical argument is very strong, that if it was going to happen, it would have happened. This kind of experiment has been going on for billions of years all over the universe, and so there's been plenty of chance if there was some route to a catastrophe to already get there.
So, Monica, why spend the $10 billion if we've got these streams of particles that are coming in that are so energetic? And actually simulate some of the same kinds of conditions, and cloud chambers have detected them in the past. Why not do something like that?
Well, I mean, I think that, like the real estate of, for example, Miami Beach would not really appreciate it if we put a massive particle detector there instead of hotels, right? So, I mean, the idea is that your cosmic ray particles, sure, you're getting those collisions all over the place, but they're taking place all over the place. And so either you put your detector one place and you wait a couple million years for the one, energetic cosmic ray to happen to pass by and kind of hit your detector, that could take a long time. So it's either $10 billion or 10 billion years. And since I don't think I'm going to be living 10 billion years, we decided.
Yeah, both these very energetic cosmic rays tend to interact high in the atmosphere, so they're not very easy to access experimentally. And as we've been discussing, you really have to sort out the details, and it's very impractical.
I mean, not that it's cheap to go into space at all, but are there places in space that would have streams of particles that...
No, it's just it's a question of volume, and when you're out in space, you just there's many energetic particles, but there's also a lot of area for them to be. And so the idea behind building a very controlled experiment is really for two reasons. One, you get it 40 million times a second instead of once every 10 billion years. and second, you are in an environment that's completely controlled. You understand the parameters very, very well of the beam itself. And that actually is very important, to really understand exactly the location of the protons, how they're being collided together, whether or not they're colliding like this versus like this. So all that kind of parameterization is very important. And kind of really makes or breaks your experiment, actually.
And, okay, I think that, for example, we know that dark matter is there because we need that to explain the way galaxies move with respect to each other, or the way they rotate and so on. But this is the amazing possibility, and I guess because human beings like to be more on the control side, is the possibility of, for example, creating dark matter in the lab, or creating these new particles in a way that we can really study them. Okay, it would be very hard for us to study them if we don't know exactly where they're coming, when they're coming, and in a very controlled way. So I guess that's the main idea of what we are trying to do here. We are trying to understand what we put in. For example, I mean, this missing energy. Okay, there are other ways that there are other experiments in the world that try to just sit there and wait for a dark matter particle hitting a target and the target moving back, recoiling, okay? Those are also other type of experiments, for example, and they are very important, okay? But here we are trying to, in collider experiments, we are trying to generate the new physics, create the new physics in a laboratory in a very controlled
And you're referring to experiments like these pools of water way underneath the Earth that would detect like a proton decay or something like that over a long time. And it takes an enormous amount of time to even go through that. And this sort of speeds up the process with these high energies. Now, you've described something, and I want to just sort of go back for a second. There is the detection of dark matter that's based on these equations of a discrepancy of energy going in and energy going out in the experiments that are already being conducted, right? But then once you detect that there must be something called dark matter, how do you actually create a dark matter particle? What would you do to do that? How would you rely on these fine
Well,
individuals here to make that happen.
If at LHC we are, obviously, if we are detecting this imbalance in energy, in and out,
Right.
means that we first created it, okay? So we first created it. And the way you do it is we are creating, for example, in these proton-proton collisions are kind of strong interactions, the basics. And we are creating a debris of particles, and because we have a lot of energy, basically what occurs is that we create some new particles, for example, supersymmetric particles that are kind of on the heavy side of where, this big ladder of supersymmetric particles, and they start going or transforming, if you want. We use the jargon decaying, but transforming into the standard model particles plus some other lighter supersymmetric particles. And at the end of this chain is where we go into the dark matter. So basically the way we create the dark matter is by producing this chain of decays, this chain of particles that finally transform into the dark matter, because the dark matter, exactly what it means, why we cannot see it, I mean, what is not luminous, is because it's neutral and is very weakly interacting. So once finally the supersymmetric chain has gone down to the lightest supersymmetric particle, that is what is our dark matter, this dark matter just escape our detector. And because it escape our detector is that we see it as missing energy.
Mm-hmm.
Okay,
if we want to study these dark matter candidates in detail, we may need to spend a few $1 billion more and build a machine that creates the particles under cleaner circumstances. Instead of colliding protons with each other, to collide electrons with anti-electrons. That turns out to be a much cleaner way to study what's coming out, and so then we could really home in on the detailed properties.
Can you do something like that at the LHC, or do you have to create a RLHC, really large? Or even larger?
Well, with existing ideas, the LHC is not quite the right shape. In fact, the predecessor to the LHC was a machine where they did collide electrons and positrons in the same tunnel. But because electrons and positrons radiate more strongly, if you try to accelerate them to the same kind of energy that these protons are, they would be very dangerous, first of all, but secondly, it would be a huge waste of energy, and it's not practical.
They couldn't be contained.
They couldn't be contained practically, right.
All right, so the whole refrigerator thing is not going to work for electrons and positrons.
Right. So the alternative design that does work is that if they move in straight lines, they don't radiate. So this is what's called a linear collider.
Like the one they have out at Stanford.
Exactly. And you would bring the electrons and positrons moving in opposite directions along straight lines into collision.
And that would end the world.
No, I don't think so. but it could give us a more controlled environment to study these questions in greater depth.
All right, let's take a quick census of the standard. I remember when the standard model, made the quarks. All right, I mean, that's all very poorly stated, but quarks had a certain kind of symmetry to them. There was a reason why there were the number of quarks that there were, and mathematically you could explain that, and physically you could explain that. But now that we're getting beyond the standard model, I mean, we're really talking about just lots and lots of particles. Is there an upper limit to the number of particles you would expect? Are there categories that are sort of coherent in a way, or is it just sort of more and more and more and more and more, and then right at the Big Bang, there were infinite particles or something like that?
Well, there are organizing principles that make sense of this zoo to a very large extent. Symmetry is the main one, which I mentioned. So although there are many, many particles, it's similar to saying that, say, an icosahedron has many sides, because it has 20 sides. But it's one icosahedron. So if we can figure out that at some deeper level, the equations have all these particles representing different sides of an icosahedron, then even though there are 20 particles, we know it's only one thing.
I see.
And that's the spirit.
It's in here somewhere, is the idea.
Yeah,
in the icosahedron.
the more basic object to think about is not the individual particles, but the overall pattern and the structure of this totality,
I see. So
which is the icosahedron.
within this thing that we
Right.
are certain describes the early moments of the universe, there can only be the following, and we just have to
Yes.
find them all.
Right.
I see.
We get a nice, if these unification ideas are right, we sort of get a coherent census of everything that there is, and we know it's everything.
All right, so we've already talked about the sort of, I gather, silly idea that the LHC would rip open reality, et cetera. Let's talk about something maybe a little more practical, and that is, what is the worst case scenario for physics that the LHC doesn't detect or doesn't find anything, or 5 years from now, we actually have a lot of biologists up here because we're tired of physics at the World Science Festival. So what is the worst case scenario? And let's just start with you, Jennifer.
Well, for me, it's a little different because of the focus of my experiment is the primordial soup, and we know it exists, and we're really trying to study its properties now. So we have, I would say, more job security in that sense. So I don't know, I think maybe these guys could answer your question a little better as far as the other particles go. But I think it has it would be very interesting as well if we don't find those things. Because as Frank said, the standard model doesn't quite work the way it is now. And if you add in supersymmetry, it makes the theories work. And so if those don't exist, then it's back to the drawing board in some sense.
Well, I think the worst scenario, as far as I'm concerned, would be that the LHC sort of completes the standard model and doesn't do anything more. So in the standard model as it stands, we need this cosmic molasses that was mentioned. We don't know what it's made out of. The simplest idea is that it's made out of one new particle, this so-called Higgs particle. And that could be true, and then you've accounted for the missing ingredient of the standard model, and that would be it. And that would be horrifying. Because then we'd have learned something very profound, and of course we'd learn to live with it, but we'd also learn that nature is a real tease.
The title of your next book, perhaps.
Right, that there seem to be all these hints that we can put it together into a beautiful package and understand things more deeply, maybe learn about the dark matter, the other secrets that seem to lie beyond the standard model. So it's certainly, I hope that the LHC will take us beyond, and I also believe it will.
Marcela.
Yeah, of course I agree that, well, first of all, we need to find the Higgs, because, although we always, or something that does its job, okay, because we would like to understand what is the origin of mass of all the particles we have seen so far. I am very optimistic that because of a lot of what the theories tell us, we need to see something beyond the Higgs. I mean, even if we see something that looks like a standard model Higgs, which is quite plausible, and the standard model will be kind of complete in its own there, okay? There's the question of dark matter. I mean, there are really experimental issues there that we already have learned about. And there's the issue of the matter-antimatter imbalance in the universe, the fact that the universe is mostly made of matter, and that's the reason why we are here rather than not, okay? Originally, we think at the beginning of the Big Bang, there was an equal number of matter and antimatter. It was annihilated. When matter and antimatter gets together, kaboom. And so at some point, something happened. There was some asymmetry, okay, that made that a bit more of the matter stayed alive, so to say. And so there's not only radiation, but we are here. Okay, so we are here, so we're the proof that there is more matter than antimatter. And so we need to understand that too, and the standard model doesn't have an explanation for that. So we don't understand what is dark matter. We didn't even get into dark energy, and let's leave it there for the time being.
You got a little time.
And so we don't understand what dark matter is made of. We know it has to be something beyond what we know, and we don't understand why we are here. And we know that there must be something beyond what we know to explain that we are here. Okay, so I think that the LHC will, for sure, shed some light about these questions. Maybe not at the level that we would love. Okay, but that's good because then our jobs are secure.
Monica?
Well, I think there's pretty much two scenarios where I would end up at McDonald's, and that is that if we discover the Higgs and the Higgs only, which is Frank's worst case scenario and also mine, which is basically means that the standard model from the experimental point of view is extremely frustrating because it's very, very well tested. We've been testing it with multiple accelerators for the past 30 years, and it has stood up to the test. A lot of these phenomena that we don't understand, like dark matter, for example, that's coming from cosmology. That's not something that, in terms of collider physics, is a problem in collider physics. So far, every collider experiment we have is really, has predicted this, and we measure it. Standard model predicts this, and we've measured it. Standard model, and so
the success is our curse.
Yeah, success is our curse, exactly. And so I think from the experimental perspective, we're really sick of the standard model. So to just continue to measure the standard model, which would be a Higgs and Higgs only scenario, would be frustrating. The second scenario, which I think would be just bad for the experimental community, is if we discovered nothing, if we had no Higgs. Now, no Higgs would be theoretically very exciting because you need this cosmic molasses to make things work. And so if it didn't exist, these guys would be in a lot of trouble, and they would have to go back to the drawing board to figure out what's happening. But experimentally, if you kind of say, oh gosh, we didn't discover anything, how about 20 billion?
Yeah, that's going to
people are going to die. They're going to like, no.
But if you go down the West Side Highway, Goldman Sachs has a building down there.
That's right.
Yeah. 200 West Street. All right, so then this is very exciting and very scary at the same time. Before I ask whether this sort of represents a kind of golden age in physics that really sort of sets our era apart from even the pre-Copernican times, is the Higgs, the cosmic molasses that you're talking about? I noticed that the title of one of your books relates to the whole supposition in the early part of the 20th century that there was something called the ether, the cosmic ether, and that you kind of needed it to make the whole thing work, and that theoretical physicists came around and said, no, actually, this ether idea is something that you need psychologically. There's no evidence that it exists. Is there a possibility that this cosmic molasses is just a kind of a psychological crutch that we may discover that we don't need, or is there a real chance that physical evidence of it will be found?
I mean, at the very least, it's been a crutch that's enabled us to run the 100-yard dash in 9 seconds. It's enabled us to make very precise equations and very precise predictions that have turned out to be true. So it's assumed a kind of reality that I think is not just a whim. I mean, it really has lived up to a very high scientific standard of proof. But we're not satisfied with kind of this theoretical proof. We want to actually produce the particle. And as I said, we don't know if it's one particle or several particles, but there's some combination of things that has been making our equations work. And we want to find out what that substance is. I like to compare it to saying, and this gets to your question of whether this is a special time in history. I think it's a very special time in history. It's as if we're fish who've suddenly discovered that they live in water, right? That what we thought of as emptiness is actually a substance that is complicating our description of the world, but we want to find out what this substance is, and we will.
And so you're the fish that's down under the water going, if you go down to the bottom, there's this hard stuff.
Yes.
I predict that out of the water, there's more hard stuff. and even stuff called like gas up in the atmosphere. And all the other fish kind of laugh at you, and they try to figure out how would we predict that.
Right.
But that's basically what you're talking about.
Yeah, and the LHC is a device for sort of ruffling up the water so that we can study the waves, or focusing in on the water so that we can see what the atoms are, and the molecules. It's very much like that.
If the best case scenarios come true on the LHC experiments that you're talking about, if the really exciting stuff happens, would it prove string theory? Would it end this sort of angry sort of controversy and argument that goes on between the string theorists and the people who think that it's just gone beyond the edge of the horizon?
Well, this is obviously the question that I think we would like to pose in a different way, because I think that string theory is an amazing mathematical tool that allows descriptions of very interesting processes, and we want to know if really we can prove the physical effects at LHC. I think that my personal opinion that from LHC we are not going to have a definite proof of string theory is there or not, or is correct or not. However, I would say that both supersymmetry or theories of extra dimensions are within the realm of superstrings. Okay, so if any of these options, and I think that I wouldn't give them equal weight, but if any of these options we get a hint of any of these options at LHC, it would certainly be very encouraging for superstring theory. I don't think we will be able to prove that superstring theory is the right description of nature at LHC, but we will be able to get superstring theories very excited. And
indeed, experimental results to prove aspects of relativity theory continued long after Einstein's death, in fact. So, I guess one evidence of the revolution in physics is the fact that both of you, your careers will be spent, in your case, taking Polaroid snapshots of the Big Bang, primordial soup, and in your case, wiring 3,000 miles of cable to make sure these detectors work. Did you envision what could be, assuming you don't end up at McDonald's, a lifelong career in physics when you started in science?
From the beginning, no. I mean, actually, I hated physics. And the only reason I got into physics was because I had two options for a summer job once in college. One was just to work in a physics laboratory assembling some photomultiplier tubes, which is a type of detector, and like sweeping out houses before they put up drywall. And so I kind of was like, drywall, air conditioning in a physics lab, drywall, so, and that's kind of how I got hooked. So it was completely through the back door. And I think, the aspect of the science that interests me the most, and I think, the theoretical aspects and all the big questions that we're trying to answer is, of course, fascinating. But I think there is a difference in my mind between physics and doing physics. And the aspect that I love the most is actually doing physics, which is the great, we've got this Higgs particle, how are we going to detect it? How are we going to build that 7-story detector? Why 7 stories? Why not? Why this way? Why not that way? And actually, trying to figure out the best way to detect all of these particles, so that all these theories that get thrown at us, we can be like, okay, we can detect that, and coming up with the most universal detector that you can find for 10 billion.
But basically, your job day to day is more along the lines of, we're getting a voltage surge on line 307B. Better ask Monica. Is that kind of?
Yeah, actually, that's kind of that's pretty. Well, I mean, it's a lot of it's kind of a nice balance, I think, because the job is kind of divided into two parts. In one side, you have a bunch of data that's coming through that you're trying to find, search for this needle in the haystack. And so a lot of that is computer work. You're sitting in front of a computer. You're trying to, comb through these, 40 million events per second and trying to find the ones that you're interested in. And there's a lot of, understanding of what's going on there. But on the other hand, sometimes when you're just really frustrated with the computer and your code's not working, then it's kind of nice to be able to go down and cable. You know, it's a great bicep workout. I totally recommend it. You know, I mean, it's like, you know, you're underneath, you've got your hard helmet on, you know, it's dusty, you're not pulling cable, you're cussing, everyone's cussing, you know, it's
I can totally relate to that.
Yes.
That's fantastic. And Jennifer, in your particular case, you know, I don't know if you have kids or a niece or a nephew or young people in your life, but I mean, do you ever get to the point where you could explain what it looks like, this first moment of the Big Bang with all your work? And you will be spending your life doing this.
I do try. I have a 1.5-year-old daughter. She's not quite ready to have that conversation yet, but
she's a little primordial herself.
Yes. But I definitely do like to talk about this stuff with other people and find ways to explain it, you know, to someone who doesn't necessarily do it every day, 24 hours a day. But I had a similar experience as Monica, a formative experience in college. I always loved science, but never thought I was good enough at it. And I had a summer job working at Stanford Linear Accelerator Center, and I loved what I did. I put together a detector. They were trying to build a detector and understand something went wrong with it, and they couldn't figure out why. So they said, okay, build a small scale version of this detector and destroy it for us. And tell us what exactly caused its destruction. So do some systematic things to it. And I just had such a great time doing that. And I realized that even if maybe I wasn't, so I'm an experimentalist, not a theorist, that even if I wasn't as good at the mathematical side of things, I really could do the experimental side very well. And that research experience made me want to pursue this career, and I haven't looked back.
You know, one would get the impression, Frank, from this panel that all the tension and anxiety that I've read about concerning the experimentalists and the theoreticians has gone away in this era, and that's really the revolution that we're witnessing on the stage. Is that true, or is there still a little bit of tension there?
Well, right now we're fine.
Should we all hug? Should we do some like hugging here?
No, we're always we're in the same enterprise. I think what happened because of our success, really, with the standard model being so overwhelming, is that theorists got way ahead of experiment and built speculative models that got beyond what could be tested. But now I think the experimentalists are catching up. They with this LHC, will have the right tool to address the questions where theory is now got to its limit. I think I showed you what I think of as compelling hints that there's unification and supersymmetry are on the right track, but the details are totally unclear. And while the experimentalists have been failing to improve the standard model, the theorists have also been mostly failing to improve the standard model over the last 40 years, and we've learned we need each other.
And for $10 billion to come together in that way, and as a bonus to figure out why we're here, is a small price to pay.
Yeah, definitely. I think that LHC has a real chance to answer these three questions in some way. Okay, I think that the idea of the next steps, we will know once, as I say, baby steps. We will first learn what is there at the LHC. Hopefully, we will learn something about Higgs, dark matter, maybe about this matter-antimatter symmetry. Not all the questions will be answered at LHC. I think that any of us would bet on that. I mean, because our universe is extremely complex, okay, and we already have gone through this experience that we need to understand things part by part. So obviously, we are in a decade where it's a very exciting decade, because we are going to get at least some first answers to these three very challenging mysteries of nature. And they are going to come mainly from the LHC. Maybe, as I said, the Tevatron is kicking in with the Higgs.
We're rooting for you, Marcela.
Yeah, well, they pay my salary, so I have to say that. And there is a real chance there. It's, of course, not a huge room. But I think that the LHC will open a window to a new era for high energy physics. And so we are all very excited, both theorists and experimentalists, and maybe that's why we are so happy together, because we are part.
Well, I have to say, I'm loving it. Marcela Carena, Frank Wilczek, Jennifer Klay, and Monica Dunford, thank you so much. And thanks to all of you. Show of hands. Anybody get lost a little bit during that? Hands up. All right. Feeling like you've got an LHC in your own garage about now? All right. Thanks so much for coming. And once again, thanks for a really terrific time.